Hello and welcome to my video. My name is David Connolly and I am an assistant professor at Aalborg University in Copenhagen, Denmark. And today I'm going to present a video to you that outlines how the existing energy system can be converted from being dependent on fossil fuels to 100% renewable energy without using excessive amounts of bioenergy. So I'm going to start by first explaining what the existing energy system looks like, so that you can see the characteristics that it has and how they have to change over the next 40 years to enable it to become 100% renewable. So I'm going to start by talking about the type of demands that we have in the energy system. So today there's three primary demands that we have from energy. First of all, we have mobility or transport. That's one key demand that we have for energy. The other is electricity. And the final key demand is heat or cooling. These are the three types of end user demands that need to be met with some form of energy today. In order to meet those different types of demands, we have different conversion technologies. And those conversion technologies, for example, for electricity, the most common one for electricity are power plants. And power plants basically convert some form of fuel into electricity. So if we then, after the conversion technology, we put the resource, then today we have some form of fossil fuel being put into a power plant, which then converts the fuel to electricity for the end user. If we then look at the heating end user demand, what happens in heat is that we have some form of individual boiler. So that can be like an oil boiler or a gas boiler usually. So once again, we put some fossil fuel into an individual boiler, and out of that we get some heat for the end user. For mobility, it's usually a combustion engine, so that could be the engine of a car or a ship or an airplane, some form of combustion engine. And for those combustion engines, it's almost always oil, and it can be gas, but it's almost always oil that's taken, put into a combustion engine, and we use that to provide some form of transport. So I hope that this breakdown of what the energy system looks like today illustrates immediately to you that the energy system is actually a relatively simple structure in terms of how fuel goes from beginning to an end user demand. So what you can probably see straight away here is that each of our sectors is very isolated from one another. Heat is provided by individual boilers and has very little connection with the electricity sector. Electricity is provided by power plants, and electricity has very little interaction with the transport sector. There is a small bit of interaction here where sometimes electricity is used to provide heating or cooling, but for the purposes of this diagram, I'm just going to leave it out so it doesn't become too cluttered, because the general principle is that in almost all cases these are very separate from one another. Another key characteristic that I want you to just look at in this system is that fossil fuels are the foundations for how everything else is designed. So if, for example, we want some electricity, we turn on a power plant whenever the user switches on a light, for example, and then some fossil fuel is immediately provided to produce more electricity. What that means is that this fossil fuel is providing the rest of the energy system with a lot of cheap stored energy. In other words, all of the flexibility in this energy system is coming from the very large amounts of stored energy contained in these fossil fuels. So in the transport sector, there's a lot of stored energy in oil. In the power plants, it's either coal or gas usually. And for individual boilers, it can be coal, gas, oil that are primarily used for the individual boilers. So in other words, because of all this stored energy in the fossil fuels, very little flexibility exists in the rest of the energy system. So for example, when somebody turns on a light, they never expect to have to wait for some electricity before the light comes on. They expect to get it immediately. And that's because of this flexibility that the fossil fuels has provided us with over the last 150 years. So taking those characteristics into account, I'm going to now start talking about how do we transition away from being this type of energy system to a 100% renewable energy system. So the first thing you can probably guess is going to happen is I have to get rid of these fossil fuels. Now, as I just mentioned, fossil fuels are the primary source of flexibility that enables everything else to function so smoothly in this energy system. So if I remove the fossil fuels, my flexibility is now gone, and I have to start replacing it with some new forms of flexibility or new forms of fuel. So the first question that would be very logical and that people often ask is there any direct replacement for the fossil fuels that we can just use that is sustainable? And the one common thing that's usually promoted is bioenergy. And this is a very good solution in many ways. Bioenergy is very similar to fossil fuels in the sense that coal can be replaced by biomass, gas can be replaced by biogas, and oil can be replaced by biofuels such as biodiesel and ethanol, which means that if we replace fossil fuels with bioenergy, then the job is done. We're now 100% renewable, and we can use all of the existing infrastructure in the same way as we used to have fossil fuels. The big problem, however, the reason that this isn't possible is that there simply isn't enough bioenergy to simply replace fossil fuels altogether. A lot of it can be covered, but if we want to use the same amount of energy as we do today in the future, then there wouldn't be enough land to grow or develop all the bioenergy we would need without having severe effects on things like food production. And that means that yes, bioenergy can be part of this solution, but it definitely can't provide all of the solution because we're limited in the amount of bioenergy we can use. So then the next question is, if we have a limited amount of resources available, can we start to make this energy system much more efficient? Now, one obvious way we can do that is we can reduce our demands here on this side. So we can reduce the amount of heat we use, we can reduce the amount of electricity and transport that we use. In the future, it's likely that we can have significant reductions of up to about 30 or 40% in our heat demands. We can reduce our electricity demands maybe by 10 or 15%, but our mobility is surely going to increase in the developed world, especially as we go into the future. So there's definitely potential here to reduce the demands, but definitely not enough to still have a sustainable amount of bioenergy that we need. So let's say step number 2 is reductions. So we're going to have reductions in heat, we're going to have reductions in electricity, and we're going to have reductions in mobility. I would call this more efficient rather than reductions, because we're probably going to travel more, but we can do it in more efficient ways, maybe by increasing public transport and so on. But in any case, we're making the system more efficient and using our energy better at the end user level. When we do this now, we require less bioenergy, but as I said, it's still not enough. We still need to do other actions. So let's start looking now at how the conversion process can be altered so that we use a sustainable amount of bioenergy. And the first simple step that can happen is that when power plants produce electricity, usually about 60% of the energy is wasted as heat. And today in most developed countries, that heat is simply put into a river or into the sea. And instead of putting that heat into the river or the sea, we can connect that heat to the heating sector so that we can make our overall system more efficient. So instead of using power plants, we can convert those power plants in my step 3 to something called combined heat and power plants, CHP plants. These CHP plants don't just produce electricity, they also produce heat for the heating sector. So we then have to construct a district heating system, which is a pipeline of hot water that connects the surplus heat from these power plants to the end user heat demand. This means that instead now of having power plants that are 40% efficient, they're now about 90% efficient, because we're using all this waste heat to meet our end users' demands. So that means we've now made the system more efficient by constructing this district heating system. The other very important thing that we've done by developing this piece of infrastructure is we've opened up the possibility to use new resources. So now that we have this district heating system in place, we can then build large-scale solar plants, we can build some geothermal heat plants, and we can use some surplus heat from industry or waste incineration. These are all new sources of heat that can be utilized in the energy system. And this is very important because using these new resources once again reduces the pressure on my bioenergy demand. So I'm now getting all of this new type of heat into the end user's demands. So number 3 is connecting the electricity and heat sectors together via district heating system, which makes the system more efficient, and it opens up the possibility to use some new resources. When I do this, the pressure on the bioenergy will be reduced, but as I mentioned earlier, we're still not at a low enough bioenergy level to have a sustainable amount. So now we need to introduce some new resources on top of these. And the new resources I'm now going to add are wind and solar electricity production. So this is the new type of resource that's going to form the backbone of my energy system in the future, and these resources produce electricity. So I'm going to connect these now to the electricity sector. So these new forms of electricity production can reduce the need for bioenergy, but they come with one significant drawback, and that's their intermittency. So wind and solar are not available all the time. This means that I need to start creating some really flexible solutions in my energy system so that I can accommodate for this wind and solar power that will go up and down throughout the day, throughout the year. So in order to do that, one of the very first steps I can do, I should just mention that these CHP plants can be flexible to a certain extent, but that means that you can only integrate about 10%, 10 to 15% of your electricity sector with wind and solar. In order to let these CHP plants operate in a more flexible way, they should have some thermal storage on the district heating system. And thermal storage is a very well-known and developed technology that's extremely cheap. So if I put some thermal storage as my step 4 on the energy system, now I can operate these CHP plants so about 20% of my electricity can come from wind or solar. Thermal storage, just to give you an example, costs about 50 times less than electricity storage. So this is an extremely cheap way of introducing some flexibility into your energy system. So now I'm really kind of starting to connect the electricity and heating sectors together. I'm using the CHP plants to produce some heat, and I'm also using the heat storage to create some flexibility to allow me to use more electricity from wind and solar in the electricity sector. So step 5 then, I've now got, at this point with all of these changes, I can use about 20% of my electricity can come from wind and solar power. But I need to come up with other ways of making the system even more flexible so that I can increase that amount and thus reduce the demand on the bioenergy on this side. So the next step that we would recommend is that number 5, you introduce heat pumps. And heat pumps are an extremely efficient way of converting electricity into heat. So they consume some electricity, and for every 1 unit of electricity that the heat pump consumes, it usually produces about 3 units of heat. Now this is extremely important because not only have I introduced a very efficient way of producing heat, I've now connected wind and solar directly to thermal storage via the heat pumps producing heat on the district heating system. In other words, wind and solar power now have access to very large and cheap amounts of energy storage in the form of thermal storage. So electricity can be produced from a wind turbine, and maybe the wind is blowing a lot so it doesn't need all that electricity. That electricity can be used to power a heat pump, which produces some heat, and that heat is then stored in thermal storage until it is needed. These heat pumps don't just go in the district heating systems, they can also go in the individual buildings. And there's also thermal storage in the individual buildings. So this means that in the future, if we have a smart energy system, if you live in the city, you'll probably get your heat from a district heating system. If you live in a rural area outside of the cities, you'll probably get your heat from an individual heat pump that's constructed inside your home. This means that we no longer need the individual boilers relying on the biomass or the bioenergy, because instead we're using these very efficient heat pumps that get their energy from much more sustainable wind and solar power. There may be some cases where people have very cheap access to bioenergy and therefore it makes sense that they have a biomass boiler in their house. But in the majority of cases, we won't have cheap access to bioenergy and instead we'll have a heat pump that depends primarily on wind and solar power. When we introduce these large heat pumps in the district heating system and these small heat pumps in the individual buildings in the rural areas, we can now introduce about 40% of our electricity can be produced from wind and solar power. So we now have enough flexibility by connecting the electricity and heat sector to one another so that about 40% of our electricity can come from wind and solar power. And that's a really good progress compared to where most countries are at today. So now we'll move on to the next step. Now that we have kind of used as much flexibility in the electricity and heat sectors through the use of thermal storage and heat pumps and these new resources, we can now focus on how can we combine the electricity and mobility sectors so we can get some extra wind and solar power onto our system and reduce the need for bioenergy. And the first key step in this process is the introduction of electric cars. So if I call them EVs, is the common name for that, where I produce electricity and from the electricity I power an electric vehicle which can meet some of my transport demand. So these electric cars, and I should stress that I'm now only talking about cars, individual cars, we expect that about 70 to 80% of existing vehicles can be replaced with electric cars by 2050. We've now connected wind and solar power via electricity through an electric vehicle to the mobility sector. And this is really important because now I'm replacing liquid fuel that would otherwise have to come from either oil or a biofuel. So I'm replacing the liquid fuel from a combustion engine with electricity that's produced via wind or solar power. So this is my step number 6, electric vehicles. When I do this, these electric vehicles have batteries, which means they introduce some flexibility, which means it's easier to integrate more wind and solar power. So when I've carried out all of these steps that I've presented to you so far, you could provide about 55 to 60% of your electricity demand from wind and solar. And when I say 55 to 60%, I also am including the extra electricity demands we have from the electric vehicles and from the heat pumps that we've introduced into the system. So now we're at a situation where we have quite a lot of renewable energy in our end user demands. Our heat sector now is very renewable with a lot of bioenergy in the CHP plants, wind and solar in the heat pumps, lots of flexibility going on with the thermal storage. And we've also introduced some renewable energy in the individual cars via electric vehicles. The big challenge when we get to this stage of transition is replacing the energy dense fuels in the trucks, the airplanes and the ships. So how do we replace those liquid and gas fuels that are used for the heavy transport like trucks and airplanes and ships? And the key technology that we see in providing this is something called synthetic fuels. And these are a type of fuel that use electricity. So to create a synthetic fuel, I use some electricity. That electricity produces some hydrogen. I combine that hydrogen with some carbon that I capture from a power plant, for example, or from industry, or from a bioenergy source. So I produce some hydrogen with electricity, combine it with some carbon, And from that combination of carbon and hydrogen, I can produce some form of hydrocarbon which goes into a combustion engine. So it can be a liquid hydrocarbon like oil is, it can be a gaseous hydrocarbon like natural gas is. And so in other words, what I've done now is I've connected wind and solar to the heavy duty transport via the production of synthetic fuels. So I'm now connecting an intermittent renewable resource like wind and solar to heavy, dense, energy dense transport use. So these fuels here are currently only at demonstration stage, but most of the individual technologies required to produce them are very much on the way to development. So there's different places that the hydrogen will have to come from electrolyzers that use electricity from the wind and solar, and the carbon can come from a variety of different sources, such as biomass, such as industry, such as the air, such as the power plant exhaust, and so on. Now that means that one really significant change that has happened here is I'm now able to get my very sustainable wind and solar resource into the heavy duty transport and significantly reducing the dependency on bioenergy or today fossil fuels. But the other very, very important side effect is that when I do this, when I produce these fuels with electricity and so on, I now get access to fuel storage. And this is extremely important. I can now use fuel storage in my system. Now by fuel storage I mean, for example, today we see a lot of big containers that contain oil, large amounts of oil. And these big containers contain a very large amount of energy. So in, for example, Denmark, there is 50 terawatt hours. That's 50 terawatt hours of oil storage in Denmark. At the same time, Denmark's annual electricity demand, the total amount of electricity that's used in Denmark all year round, is about 35 terawatt hours. That means that there's more oil storage in Denmark than the total electricity demand consumed over the whole year. Now this is very significant because it means that when I connect the electricity sector to synthetic fuels and the fuel storage system, I now have introduced huge amounts of flexibility within the conversion side of the energy system. So when the wind is blowing too much, I can easily produce some synthetic fuels which I can then put into a storage tank and keep for a time that I need them. I've now connected intermittent resources to an extremely large amount of cheap, affordable energy storage. So this flexibility that I removed when I got rid of the fossil fuels has now been reintroduced in the conversion end of the energy system, where I can now easily integrate very large amounts of wind and solar due to all of this flexibility that I've now reintroduced back into the system. When I do this, step number 7 that I've now changed, I can now supply approximately 80% of my electricity demands from wind and solar. And that's 80% of the total electricity demand, so it includes the extra electricity that I need to produce these synthetic fuels. You can now see that the energy system is far more complex, especially in the conversion side of the energy system, than it was when we began. And we estimate that using the energy plan model that we've developed at Aalborg University and this concept of smart energy systems, which we try to model and analyze, that we can achieve a 100% renewable energy system without overusing the bioenergy resource we have available to us today. And we can do that without increasing the costs of energy in the year 2050. We estimate that a maximum increase of about 10% in our energy costs will occur, but that's been very, let's say, on the pessimistic side. There's many assumptions that indicate it may be a relatively similar price for our energy in the future as it is if we depend on fossil fuels. So the first thing I want to emphasize once again is that this is a 100% renewable energy system that uses so much wind and solar that we don't overconsume the bioenergy resource. The next key point is that the cost of energy in this system is not significantly higher than the cost would be if we stayed relying on fossil fuels. And the final very important point that you need to acknowledge when you see this type of system is that the costs might be relatively similar, but the structure of the costs has changed dramatically in this system compared to a fossil fuel world, especially if you're living in a country or a region that imports lots of its fossil fuels. For example, if we take the European Union, right now the European Union imports a lot of its fossil fuels into the region. This means that a lot of money is exported out of the European Union to other countries where we need to get those fossil fuels into the European Union. In contrast, if we have a smart energy system, very little of the energy system is dependent on fossil fuels. In fact, in this situation, we have no fossil fuels. And instead, we're depending on local bioenergy, which is developed inside the European Union. We also have a lot of infrastructure that we're now developing locally. So instead of spending money importing fuels, we're now spending money developing local infrastructure. We're building new CHP plants, we're building new supplies of heat, building new supplies of electricity, building new heat pumps in the buildings, making the buildings more efficient, reducing the need for oil by developing some electric vehicles, building new synthetic fuel plants. These are all local investments. So we expect that even though the costs of the energy are very similar, the amount of jobs that you create with a smart energy system far exceed the amount of jobs that currently exist in a fossil fuel energy system. And that is really good news, because it means we can be 100% renewable without overusing our bioenergy. We can do that without significantly increasing the costs of energy, and we can do it while creating a lot of local jobs. This is the type of analysis that we quantify in our research group at Aalborg University, and you can read many of our publications on our website energyplan.eu. You can also freely download the model we have developed to model these types of energy systems and perhaps carry out a smart energy system analysis of your own country. Thank you for listening, and I hope you enjoyed the video.